you and Professor Yoshida for organizing this very interesting forum. It's been very inspiring so far, and a very nice opportunity for exchange. As you may know, at Deltaris, we're not a university, but we're trying to get developments from academia into practice. So we're very interested in all of your work. We've only recently started to more intensively work on data-driven and probabilistic site characterization, because we see a lot of demand for that in our, let's say, Dutch geotechnical practice. Many people go into reliability-based design and assessment of structures, and they are really looking forward to more accurate characterization of their inputs for these analyses. So we're looking at all of your work with a lot of interest, and I think now we're in a pretty steep learning curve. Also, many thanks to Jenye for his advice and support over the last month in our developments. And Antonis will now share some of our latest developments and experiences with you. So thanks a lot for the invitation.
Thank you, Timo.
All right. Can you hear me? Can you see my screen?
Yeah, I can hear you. I can see the screen.
Great, perfect. And thank you, Timo, for the introduction, and thanks everybody for us participating in this forum. So in this presentation, I'm going to show you a framework that we have been working together with Timo Svekenik and Eleni Smirniou in Deltares, and of course in close discussion and coordination with Gianni Ching. And I will start immediately. So this is the table of contents for today's presentation. So I will start with a small introduction of our framework, and then I'm going to show you how it performs in 3 different example cases. And in the end, we're going to discuss some conclusions, next steps for development, and of course, we would be glad to hear your feedback and questions. So starting up, framework is named BASIC, which stands for Bayesian Site Characterization. Its purpose is to perform Bayesian updating of engineering knowledge for soil using site investigation data, and to provide inference and predictions of soil parameters on a probabilistic level. To do so, it performs operations that allow for the identification of the parameter relationships, the identification of the soil heterogeneity pattern, the derivation of the posterior PDFs of soil parameters, and we wanted to be able to extend into hierarchical Bayesian models. I have to note that at the heart of BASIC lies probabilistic programming. And just to give you a very short introduction, description of it, probabilistic programming is the programming paradigm that allows us to build very flexible and intuitive probabilistic models. So as a very, very short example, if we wanted to perform a Bayesian linear regression, I think that, well, this is what we would write on a blackboard, right? Can you see my mouse?
Yes, yes.
Yes.
Perfect. Great. So this is what we would write on a blackboard, and then perform Bayesian linear regression, as you see here, with the posterior lines being close as a bandwidth around the true regression and matching the data. Now, this set of lines are very easily written into probabilistic programming script. The script more or less looks exactly what we would put on a blackboard. And as you can imagine, this makes things very intuitive, flexible, and I also hope to show that it's becoming an efficient and effective approach. So the first example I would like to show you with BASIC is just a 1D case. It's actually based on the type A site investigation case that is also presented in the paper of MusicX by Professor Ching and Hun. So a small description of the problem here. We assume that we have at the exact same location a CPT and a borehole. This is not very realistic, but well, let's just pretend that the horizontal scale of actuation is just very, very high. So the CPT is almost a continuous measurement. It has measurement intervals of 10 centimeters. On the other hand, we have 4 parameters that are estimated at the borehole testing through lab tests on samples taken by the borehole, and we only have 8 measurements per parameter. Now we make the assumption that the parameters follow a multivariate normal distribution, and to be exact, not the parameters themselves, but the transformation of the parameters. The objective of this study now is to perform a Bayesian updating of the mean and covariance of the multivariate posterior PDF, and also to derive the conditional random field credible intervals given the data. So just to keep it very simple, we have to perform inference on the red points, and then using the data of the blue points, make predictions for the other parameters at those depths. Using BASIC, we can derive the posterior of the mean of the distribution and the cross covariance. And the reason I'm showing these plots here is to keep in mind that the mean and the cross covariance are described now by distributions. So we have a posterior distribution, not just a signal value. And the black lines are actually the true values. The next step is to create the credible intervals of the parameters, and this is how we do it. In total, BASIC needs 1.5 minutes of training and prediction time to do that. Now, this was a very simple case, so it was like a warm-up, like a proof of concept of the framework. The next step is showing how it performs in the benchmark example, which is in 3D now. So again, we use BASIC to perform inference on the data, on the training data. We started with case G1, which was the simplest one, and the large training set, so set 3. We perform inference, we derive the posterior of the mean, the covariance between parameters, the horizontal and vertical scale of fluctuations, and then we perform a prediction at the validation test location, at the validation locations, and we get this mean prediction here. The red line is the mean prediction, the black line is the validation data. And you can see that both of them are quite close, and those are the indications of the RMSE. This is without splitting the layers. So we don't take into account that we should be using different parameter distributions for every layer. So this is the QT. This is the prediction of the mean prediction of the IC, and the IC is not. We do not perform inference on the IC itself, but we perform inference on the QT and FS, which are cross-correlated, and then we calculate the IC with those predictions. And of course, the SBT. So we also run the same framework for G2, and then we can compare like that to the benchmark example for training set 3. But then we also took a next step. We believe that having 3 different layers means that we should have 3 different sets of distributions. So then we start splitting the layers of the training set, and of course during training we know what where every layer, in which layer every point belongs. So we can derive the posterior PDF of the mean QT, FS, vertical and horizontal scale of fluctuation per layer, and then we can use those for prediction. Now, we might have some inaccuracy in identifying the horizontal scale of fluctuation. It's not that far off, but it's not as accurate as the vertical scale of fluctuation. And probably this is because if we plot the density, this graph shows the density plot of the horizontal distances per layer, and you can see that most of them focus in the area of 0 to 10, while the scale of fluctuation true value is 10 and 15. So this makes some sense into why the horizontal scale fluctuation prediction is not that accurate. So now we have 2 different approaches to how predictions should be made using multiple layers. One of them says that the layer is defined by the SBT value. And so in this case, we say that we already know the layering of the validation set. This is something we didn't develop yet. We are working on it, and we are following a lead to fix it. But for now, let's say that we already know the SBT over the validation location. And in this way, we can have predictions with, for example, a pocket of silt into the sand layer. So in this approach, this is allowed. The other approach we have is to define strict boundaries between layers and follow the geological formations. So we don't really follow the SBT prediction, but the SBT indication, and we cannot allow pockets of one sand to infiltrate the other sand, the other layer, of one layer to infiltrate the other layer. So this is the mean prediction in this approach, and the greatest benefit of going Bayesian is being able to define the 95% credible interval, or in other words, that everything is defined by probabilities. So now we can solve the interval at every depth, at every location, which implies that there is a Gaussian distribution at every depth. And you can see that the interval can grasp, can envelope the data quite well in most cases. This slide shows how the mean prediction performs for the case of G2 by splitting layers according to the SBT. And then we have a comparison of the methods. So I would say that the last two approaches are not directly comparable to the rest because layers are taken as knowns. But I think they also provide some insight about what we can do once we start implementing Bayesian identification of the layers. Finally, we have used BASIC in a different setting. So this is still a 3D problem, but now we also have to deal with sparse data. So we used the Baytown site investigation dataset, which was shared and inspired by Professor Tsing. It was handed to us by Professor Tsing. And well, just to give a description of the problem here, in our domain, we have 9 CPT test locations and 5 borehole test locations. And as you can see, most of the CPTs provide very dense measurements, but the boreholes are pretty much empty over depth compared to the CPTs. So this leads to very sparse covariance matrices. Just to give you an indication, the covariance matrix is bigger than 8,000 by 8,000, while the non-empty cells in this matrix are around 600 by 600. You can get a good grasp of what's happening by having a look at the autocorrelation matrix. So you can see that there are many points that have 0 to 0.2 autocorrelation, which means small to none information gain from those cells. And this is because they are either too far apart in the horizontal or in the vertical direction. So their autocorrelation is very weak, and they cannot really influence that much each other's values. So in order to be able to solve, pass around this problem, we use the flexibility of BASIC to redefine our likelihood function. So to do that, we have to start with some assumptions. First, we assume that the CPT measurements are the ones that define the determination of the vertical scale of fluctuation. And this is largely true because the borehole measurements are too far away from each other in relation over depth. They're too far from each other in relation to the vertical scale of fluctuation to be able to influence it greatly. And the second assumption is that the vertical scale of fluctuation doesn't influence the determination of the borehole parameter distributions for the same reason. So now we have a likelihood function that is split into 2 components. It's a sum of 2 components. The first component is about the likelihood of the vertical scale of fluctuation and the mean and standard deviation of the CPT measurements at every CPT location. The second component is the likelihood of the horizontal scale of fluctuation and the mean and covariance matrix of all parameters, so borehole and CPT parameters, at every depth of the domain. So now, this is the formulation of the likelihood function, and we understand that it's not theoretically 100% accurate, because summing up terms implies that they are independent. So we are assuming independency between CPT locations. We know this is not true, but also we know that the correlation is not as strong as it is in the vertical direction. So right now we're in the process of assessing the validity and the inaccuracy of this likelihood formulation. However, we have seen some benefits stemming from this formulation. So BASIC can solve this problem in more or less 15 minutes, and it can provide a multivariate PDF between all variables. Again, Y1 to Y8 is a transformation of the CPT, and Borel parameters. We can provide the pair plots between all parameters. And just to keep something in mind, those points are not always in the same location. So this means that the true covariance between the points is actually their cross covariance times the autocorrelation between their locations. And once we make this transformation on the pair plots, you can see that the PDFs start matching the data much better. So this PDF is transformed to this shape. One more thing is that Basic was able to derive the posteriors of the vertical and horizontal scale of fluctuation. And this is important because the approach that didn't really cherry pick valuable information using the redefined likelihood formulation was not able to derive a good posterior for the horizontal scale of fluctuation. And most likely this occurred because the important information was lost into the noise of a very big sparse matrix. So summing up, I hope that this presentation makes clear that Basic can be an effective and efficient framework for Bayesian site characterization. And I hope we can also present that its intuitive nature and flexibility allow for shaping Bayesian models according to the problem's needs. So Basic is also able to incorporate prior knowledge. This is particularly helpful if we have large databases available, or even databases that are closer to our site, or even hierarchical Bayesian models available. And just to make a notice here that the results we saw today were derived using uninformative priors. Another benefit is that all variables can be considered uncertain and inferred by the data, but at the same time, we can include engineering insight to improve performance. And last but not least, a very important aspect of going Bayesian is that we can offer results in a probabilistic level, which is in contrast to what happens with typical machine learning approaches. So this leads to benefits into the determination of characteristic and design values, providing input to reliability analysis, and gaining insights for concepts such as the value of information analysis or smart site investigation. Just like indicated through the main body of the presentation, our next steps lie into layer identification. So we are working on how we can perform Bayesian site characterization while also identifying the layer in a Bayesian setting. Again, checking the validity and the inaccuracy of the problem-specific likelihood function, and also making some more progress into integrating Basic with hierarchical Bayesian modeling. So this was it, and I will be glad to hear your questions now and your feedback.